All right, today's notes is going to be on 2.4, part 2, the chain rule. So this is the second part. We're going to go ahead and we're going to start off with an example. I want you to take the derivative. Remember, if it just says differentiate, that also means to take the derivative. So on this one, 3x squared is going to be the argument. Now remember, always take the derivative outside. Well, the derivative of y is going to be a y prime. The derivative cosine is going to be a negative sign, and then you keep the argument the same. Now I took the derivative of the outside. Now I have to take the derivative of the inside. And the derivative of the argument, the derivative of 3x squared is going to be a 6x. Do not multiply the 6x inside the argument. I'm going to go and I'm going to move the 6x to the front. So it's going to be a negative 6x sine of 3x squared. Now B looks somewhat similar to A. Right here, the argument was 3x squared. On this one, the argument is 3x. What I'm going to do is I'm going to rewrite this. I'm going to write this as a y equals cosine of 3x, and then I'm going to put the square on the outside. So now I'm going to go ahead and I'm going to do the chain rule. The derivative of y is going to be a y prime. Now remember, always do the outside. So I'm going to go and bring the 2 out to the front. And now I have a cosine 3x on the inside because you keep the inside the same. And then decrease the power. So when I decrease the 2, it turns into a 1. Now that I took care of the outside, I'm now going to take the derivative inside. So right here, if you notice, you have a cosine of 3x. So I'm going to take the derivative of cosine, and the derivative of cosine is going to be a negative sign. Keep the argument the same, though. Keep the argument the same. Well, now I have to take the derivative of the argument. So I'm doing like the chain rule like 2 times. So now the derivative of 3x is going to be a 3. So once again, what I did was I started on the outside. I brought the 2 out to the front, kept the whole inside the same, decreased the power. Now that I took care of the 2, I'm now going to move on the inside. Well, guess what? You're stuck doing the chain rule again. The derivative of cosine is a negative sign negative sign of 3x because you keep the argument the same. And now that you took the derivative of cosine, now I have to take the derivative of the argument, and the derivative of the argument is going to be a 3. So right here, when I clean it up, I'm left with a negative, and then 2 times 3 is going to be a 6, and then I have a cosine of 3x and a sine of 3x. So I'm doing the chain rule inside the chain rule. This one's going to be the same thing, the chain rule inside the chain rule. I'm going to rewrite this as f of t equals sine of 4t raised to the 3rd power. Start by taking the derivative of the outside. Well, the derivative of f is going to be f prime of t. I'm now going to go and take the derivative on the outside. So I'm going to bring the 3 to the front, keep everything inside the same. Keep everything inside the same, decrease the power to 2. Now I took care of the 3. I'm now going to take the derivative inside, which is the chain again. So the derivative of sine is going to be a cosine. Keep the argument the same. Keep the argument the same. And then I'm going to now take the derivative of the argument, and the derivative of the argument is going to be a 4. So when I clean this up, 3 times 4 is going to be a 12. Now this is going to be a sine 4t squared. Typically the square is in between the trig and the argument. So it's going to be sine square of 4t. And then don't forget the cosine of 4t. We're going to move on to the derivative of the natural logarithmic function. We're going to let u be a differentiable function of x. If you are asked to take the derivative of the natural log of x, the derivative of natural log of x is always going to be 1 over x. As long as x is greater than 0, you can never take the natural log of a 0 or a negative number. Now, the chain rule also applies here. So let's say you have a natural log of u. Well, the derivative of natural log is going to be 1 over this argument times the derivative of the argument, which is du over dx. Or you could write it as 1 over u times u prime, because u prime is derivative, which basically means the numerator is u prime and the denominator is just the u. Now keep in mind that the u has to be greater than 0 because you can never take the natural log of a negative number. So let's apply this. Find the derivative of the function. So right here, we are taking the derivative of natural log of 2x. So the derivative of natural log is going to be 1 over whatever the argument is. So this is going to be 1 over 2x times, now you take the derivative of the argument, and the derivative of 2x is going to be a 2. So right here, the 2's cancel out, and your answer is going to be 1 over x. On example B, I'm going to go ahead and the derivative of natural log is going to be 1 over the argument. So the argument is going to be the x squared minus 3 times, now I'm going to take the derivative of the argument, and the derivative here, the derivative of x squared is going to be a 2x, and then the derivative of a constant is 0. So to simplify this one, the 2x is the numerator, and the x squared minus 3 is the denominator. Okay, on this one, as you can see, always start off with the outside. You're going to end up doing the chain rule here, as well as taking the derivative of natural log of x. So when we start off with the chain rule, you bring the 4 down to the front, keep everything inside the same, decrease the power. Okay, I just took care of the outside. Now I'm going to take the derivative inside. And the derivative of natural log of x is going to be 1 over x, because the argument is x. And then if you go ahead and you take the derivative of x, the derivative of x is just a 1. So to clean this up, this is going to be 4 natural log x to the 3rd power all over x. All right, before I do the next 2 examples, we need to recall these properties. Now, if you have the natural log of AB, that is the same as saying natural log of A plus the natural log of B. These are the properties of logarithm. If you have the natural logarithm of A over B, that's the same as saying natural log of A minus natural log of B. That is the quotient property of logarithms. And then the last property is if you have natural log of A raised to the B power, you move the B to the front, and that's B natural log of A. So we need to recall these properties from a previous math class. Okay, I'm gonna go ahead because a lot of times you could go ahead and you could take the derivative right now, but then you're gonna be stuck doing the chain rule in here. And remember, step number one is always try to simplify. So right here, what I'm gonna do is I'm gonna rewrite this. This is actually f of x equals natural log of x plus 2 raised to the 1/2 power. If I use this property, I can move the exponent out to the front. So this exponent, I'm gonna move it out to the front. So then f of x is equal to 1/2 natural log of x plus 2. Now I can go ahead and I can take the derivative. I'm not doing the product rule because I only have one variable. So the 1/2 is a constant. The derivative of f is going to be f prime of x. 1/2 is a constant. Now the derivative of natural log is going to be 1 over the argument times the derivative of the argument. Now the derivative of x is going to be a 1. The derivative of 2 is going to be a 0. So that's going to be your final answer. It's going to be 1 over 2 parentheses x plus 2. You could go ahead and you could distribute on the bottom and get 2x plus 4, but I would leave it like that. Now, you're definitely going to want to use the properties on this one, because if not, you're stuck doing the quotient rule, the product rule, and the chain rule. So I'm going to go ahead and I'm going to separate all these terms, okay? So I have f of x equals natural log. This is now right here, that's the product rule. So that's going to be the first step. So that's going to be natural log of x plus natural log of x squared plus 1 squared. And then because this is a denominator, this is the quotient rule. So now I'm going to minus natural log. And this is the same as saying 2x cubed minus 1 to the 1/2 power. So this is addition because I'm multiplying. And then this one is subtraction because it's on the bottom. It's a denominator. I'm now going to apply the power rule. So I'm going to move the 2 out to the front. I'm going to move the 1/2 out to the front. So here I have a natural log of x plus 2 natural log of x squared plus 1 minus 1/2 natural log of 2x cubed minus 1. Notice I have not taken the derivative yet. I'm now going to take the derivative. So the derivative of f is going to be f prime of x. The derivative of natural log of x is 1 over the argument times the derivative of the argument, which is just a 1, plus 2 is a constant. The derivative of natural log of x squared plus 1 is going to be 1 over x squared plus 1 times the derivative of the argument, which is going to be 2x, minus 1/2 is a constant. And then the derivative right here is going to be 1 over 2x cubed minus 1 times, and then the derivative of the argument, bring down the 3, that's going to be a 6x squared. So this is one term, this is another term, and then this is the last term. They are all separated by a plus and a minus. So I'm going to simplify each section. 1 over x times 1 is just 1 over x. Right here, 2 times 2x, that's the numerator, that's 4x. And the denominator is the x squared plus 1. Now right here, the 6 and the 2, those can simplify. 6 divided by 2 is 3, and the 3 is in the numerator with the x squared. And the denominator, I'm left with a 2x cubed minus 1. And that's your final answer. Do not try to reduce these because that says minus 1. Last part. Derivatives for bases other than e. So we're going to let a be a positive real number, but a cannot equal the number 1. And we're going to let u be a differentiable function. Of x. So if you have the derivative of some number raised to the x, the derivative, you guys will have to memorize this, is going to be natural log of the number times the function itself. Now, let's say that the exponent was an actual function. If you have a to the u, it's going to be natural log of the base times the function itself times the derivative of the exponent. And the derivative of the exponent is going to be the du over dx. Right here, we didn't do it because the derivative of x is just 1. The derivative of x is just 1. This is going to be our last example. So right here, we have a number raised to an exponent, a number raised to the exponent. So the derivative of y is going to be y prime. So now it's going to be natural log of the base. So it's going to be natural log of 2 times the function itself. And then if I were to use this formula, the derivative of x is just going to be a 1, which doesn't change anything. So then this is your final answer. Whenever you have an exponent, always take the derivative of the exponent. Now this one is set up like this. But remember, these are the same, just the derivative of x, the dx over dx is equal to 1. That's why we don't write it. So the derivative is going to be natural log of the base, which is a 2, times the function itself, times, now you're going to take the derivative of the exponent, and the derivative of 3x is just the number 3. Now, you can leave it like that, but typically on a multiple choice test, the 3 would be out in the front. It would be written like this. By the community of property and multiplication, you can move them places. And that's it. Here, I'll make up one more. Let's say f of x equals 5 raised to the 4x squared. The derivative of f is going to be f prime of x. It's going to be natural log of the base, so natural log of 5 times the function itself, times the derivative of the exponent, and the derivative of 4x squared is going to be an 8x. Now you can leave your answer like that, but typically that 8x is going to be in the front. It's 8x natural log of 5 times 5 raised to the 4x squared. And you cannot combine these. And that concludes our notes.